This lecture begins with the dynamics of uniform circular motion. That is, how do we apply F equals ma to such situations? Okay, I'm going to once again refer to this demonstration, which if you recall is called a conical pendulum. Let me arrange the conical pendulum like so. And then as we already know from the kinematics of uniform circular motion, the pendulum does have an acceleration, the centripetal acceleration, which is inwards towards the center of the circle. Now there are two forces acting on the pendulum. There is of course tension from the string and the force of gravity straight downwards. Those two forces have to add together vectorially by means of the equation F equals ma to give us then the centripetal acceleration inwards towards the center of the circle. So we're going to begin the dynamics here of uniform circular motion by specifically examining the conical pendulum example. Before I do, however, I have to describe to you exactly what is meant by centripetal force. Let me reposition my camera, my phone, in order to do so. Okay, so bear with me as I move this, like so, tilt it up. There we go. Okay, so what is called centripetal force? Well, what we're going to do is apply F equals ma to situations involving, for example, uniform circular motion. Okay, uniform circular motion, by the way, is abbreviated as UCM. So from now on, when you see me write UCM, that means uniform circular motion. Okay, let's say, for example, that we have an object moving in a circle, like so. Okay, right here is the radius of the circle. Here's the object itself, we'll say. See, and then right here is the centripetal acceleration vector that is inwards towards the center of the circle. Okay, now for the conical pendulum, there are two forces acting that will cause this, but then ultimately here's how we begin to write F equals ma for such situations. Okay, now the right-hand side of the expression is the same thing as it always is, the net force. However, the net force is equal to the mass multiplied by the centripetal acceleration, a sub c. The centripetal acceleration has a magnitude that's equal to the speed squared divided by the radius. And then the left-hand side of the expression is the vector sum of the forces, but specifically the vector sum of the forces in the radial direction. That is, inwards towards the center of the circle, the same direction as the centripetal acceleration. So let me write that here. This is going to be the sum of the forces in the radial direction. So what you'll see me do then, as we start to proceed through situations involving the dynamics of such situations, is that I'm going to be writing this expression over and over and over. The right-hand side of the expression here, by the way, is given a name. The right-hand side of the expression is referred to as the centripetal force. The centripetal force, however, is not an individual push or pull, like tension or gravity or something like that. Instead, it is just a name that is given to the net force for such situations, which is called the right-hand side of the expression, the centripetal force. Okay, now let's go ahead and specifically take a look at the conical pendulum. I have that set up as a lecture example. Go ahead and copy that example into your notes as I read it here. A conical pendulum's string is 1 meter long. What is the period of the uniform circular motion if the angle made by the string with respect to the vertical direction is small? I'm going to use this example, by the way, as a means of introducing you to what is called the small angle approximation. Okay, let me go ahead and erase the board here. Okay, now specifically we do get to the conical pendulum. Okay, first of all, we diagram out the pendulum as seen in profile. Okay, so right here is the length of string. The length of string is usually referred to as L. We're given that L here in this problem is 1 meter. Right here is the object itself of mass M. Notice that the object's mass is not given. Okay, now the angle that is made by the string with respect to the vertical direction. That's described in the following way. I'm going to go ahead and construct right here in profile a right triangle And this angle here we'll refer to as theta, and as is noted in the problem, the angle theta is small. Okay, now where is the circle about which the object is circulating? Well, it's actually perpendicular to the board. At this instant, the velocity vector of the object, we'll say, is out of the board like so. And so then therefore it circulates on the board in the following manner. It comes out of the board here and then goes into the board here as it circulates. The easiest way to draw that, very simply by the way, is just to do something like this. Like so, where right here is the radius of the circle r, and the radius of the circle, you'll note, is not given in the problem. Okay, now at this particular point here on the diagram, at this moment, the object does have a centripetal acceleration a sub c, which is inwards towards the center of the circle. Okay, and now we proceed dynamically as we always do by first of all drawing out a force diagram and then adding everything up by using F equals ma. Okay, as I already have noted, the tension is associated with the string like so. And right here is the force of gravity, mg straight downwards. And then we have right here the centripetal acceleration vector, which is inwards towards the center of the circle, which is over here on my diagram. Incidentally, by the way, it doesn't matter where the object is on the circle, the force diagram is always going to be the same. So think of mg and the tension vector like so, it's just kind of circulating on the diagram here as the rotation occurs. So drawing it like this is perfectly fine. Okay, now notice that the tension is on an angle with respect to the acceleration vector, so then therefore we have to break it into components. Okay, we break it into components like so, perpendicular to the acceleration and parallel to the acceleration like so, where from the geometry, as is plainly noted, this angle right here is the same thing as the angle theta. So in other words, that force diagram, if I drew it right over here, here's the tension vector, and then therefore if this is the vertical direction like so, this angle here is pretty obviously the same thing as this angle here. Okay, now we add everything up by using F equals ma. Okay, first of all, in the vertical direction, there is no acceleration, so everything cancels out. So right here, this t cosine theta cancels out with mg. Okay, and now in the radial direction, that is along the radius of the circle inwards towards the center of the circle, you'll note right here that we do have a component of the tension that points in the same direction as A. This right here is t sine theta, so then therefore we have t sine theta is equal to ma is equal to mv squared over r. Once again, the right-hand side of the expression here is what's called the centripetal force. It's just a name given, however, to ma, the net force itself. Okay, now let's go ahead and algebraically combine these equations together. We're not asked to solve for the tension in this problem, so I'm going to go ahead and get rid of it. Here's how I'm going to do so algebraically. I'm going to take the top expression here and I'm going to solve for t, and then I'm going to plug it here into the bottom expression like so. So take the cosine of theta and move it down to the denominator here on the right-hand side like this. And then take this expression for the tension T and then plug it into here. And as we do, things then start to simplify. So we get mg sine theta over cosine theta, and that then equals mv squared over r. Notice that the mass of the object cancels out. So because the mass of the object cancels out, it doesn't matter if I was using a laboratory weight or a bowling ball, for example, in this situation. Ultimately, the period, which we'll solve for in just a few minutes, will turn out to be exactly the same thing. The mass doesn't matter. Okay, let's go ahead and simplify this. Sine over cosine here on the left-hand side of the expression, of course, is equal to tangent. So we end up with g tangent theta is equal to v squared over r. Okay, now what are we asked to solve for here? We're asked to solve for the period of the motion. So let's go ahead and make the following substitution for the speed v. So from the kinematics of uniform circular motion, recall that the speed v is equal to 2 pi r divided by the period. Before I plug this into the expression, however, let's be a little bit careful here. Notice that I have two capital T's appearing in this problem. Be careful about which capital T is which. On the top board, we were talking about the tension force, which we've now eliminated from our expressions. Here on the bottom board, this is the period, so just be careful about what's what. So now what I'm going to do is take this expression for the speed. I'm going to square each of the terms here, and when I do, I'm going to cancel out a radius r. That then gets me to here. So take a look at this expression carefully. like so. What I did was I took the expression for the speed v, I squared the terms, and then I canceled out a radius like so. And then I get to this point here, and then we're kind of stuck. We're kind of stuck in the following sense. We don't know what the radius is, nor do we know what the angle is. So then therefore, what do I do in ultimately trying to solve for the period capital T? This is where what is called the small angle approximation enters the example. Let me explain to you what is meant by the small angle approximation. Okay, so forgetting about the example for just a moment, let's just say that we have a right triangle. Like so. Where right over here we'll say is an angle theta. And then we've got the opposite side, the adjacent side, and the hypotenuse. Okay, and now from SOHCAHTOA, let's take a look at sine and tangent. Okay, the sine of the angle is opposite over hypotenuse. The tangent of the angle is opposite over adjacent. However, now let's think of the angle as being small. So if the angle is small, what could you then approximately say about A and H? They're about the same thing. So then therefore, if I redraw this, it's not even really a right triangle anymore. It kind of looks like this instead. Like so, where here's O, and now we'll just call this A and A, like this, and then right here is the angle theta. So then therefore, if the angle is small and A and H are about the same thing, this then means that sine and tangent are about the same thing. In addition to that, however, recall what an angle in terms of radians is written as. An angle in terms of radians, theta, is equal to an arc length O in this case, divided by a radius A. Notice that this ratio here is the same thing as this ratio here, is the same thing as this ratio here, as long as the angle is small. This is what is meant by the small angle approximation. Theta, sine of theta, and tangent of theta are about the same thing. Okay, now how small is small? Well, as you watch this video, now what I want you to do is go ahead and get out a calculator. Okay, what I want you to do is I want you to convert your calculator, or rather change its mode, that is, into radians. So if you're in degree mode, change it into radians. And now let's pick a simple angle. Let's say 15 degrees. So I'm going to go ahead and type in 15 degrees here, a small angle, into my calculator. And now let's convert it into radians. So to convert to radians, you multiply by pi over 180. Go ahead and do so. And then if you go out 2 decimal spaces, what you should end up with is 0.26. So now what we're saying is that the angle is 0.26 radians. Let's take the sine of that while you're in radian mode in your calculator. So if I do the sine of that, and I once again round off to 2 decimal spaces, what do you get? Once again, 0.26. Okay, just take the tangent of that. If you take the tangent of that while still in radian mode, out to 2 decimal spaces, you'll get the same thing again, 0.26. So as long as the angle is small, a 15-degree angle, 0.26 radians about, then therefore the angle and the sine of the angle and the tangent of the angle are about the same thing. This is what is called the small angle approximation. Okay, here's then how we're going to incorporate this into our example. Okay, let me do some erasing here. Okay, specifically we need the tangent of the angle on the diagram above. The tangent of the angle is equal to the opposite side, the radius r, divided by right here, the unnamed adjacent side of the triangle. However, the tangent of the angle and the sine of the angle are about the same thing. So I'm going to think of this right here as the sine of the angle theta instead, which is equal to the opposite side of the triangle r, divided by the hypotenuse, the length of the string L. So let's go ahead and replace then the tangent of theta with r over L for that reason. Like so. And now notice what cancels from the expression. What cancels from the expression is the radius of the circle. And at this point, we just cross multiply a little bit, and then we solve for t squared, and then we'll take the square root of that in order to ultimately arrive at a description of the period of the rotation. Excuse me. Okay, so let's go ahead and take this guy here and cross multiply it and solve it for t squared. When I do, I end up with this expression here, like so. And now let me just go ahead and finish by taking the square root of both sides of the expression. When I do, I end up with this equation here, like so. Okay, now let's go ahead and solve for our answer here in this problem before I explain more fully what this equation is saying. What we were given in this example is that the length of the string is 1 meter. So then therefore, if I have 2 pi and then I multiply by the square root of 1 divided by 9.8, where the length of the string is 1 meter, I then end up with my period as being equal to about 2 seconds. So let me now go ahead and demonstrate this to you. With my conical pendulum, I approximately do have a length of string that's equal to 1 meter. Okay, I'm going to have to reposition my phone once again in order to do this, so bear with me as I do. Let me tilt the phone downwards. There we go. Okay, and then right here, this length of string like so, this is about 1 meter right here, like that. And then let me go ahead and circulate it like so. And as I circulate it like this, the time necessary for 1 revolution to occur is the period. That's equal to 2 seconds. It doesn't matter how big the angle is, as long as the angle is small. So for example, let's say that I have a really small angle associated with the conical pendulum, something that looks like this. And then with a stopwatch, for example, I time how long it takes for 1 revolution to occur. That 2-second time interval is the same thing as it is right here when the angle is a little bit bigger. Once again, this is still within the small angle approximation. So if I use, for example, a stopwatch here to measure the time necessary for 1 revolution to occur, it would once again be equal to 2 seconds. Now, the speed of the object here is greater than it is when the angle is smaller, say like so. And the reason for that is because the radius of the circle is smaller. But in both cases, the period is exactly the same. Okay, let me go ahead and tilt this back. And as I do, let me once again emphasize that the period only depends upon the length of string. Okay, a couple of other things here about this expression. Okay, with the expression itself, once again, the only thing that matters is the length of string L. So if you make the length of string L smaller, then the period gets shorter. I could actually just demonstrate that very quickly like this. Let's go ahead and make the L really small, like so. Like so. And the period here, as you can see, is actually quite short. Okay, then lastly for this expression, before we get to something else associated with this problem, take a look at this expression. This expression actually allows you to measure g, acceleration due to gravity, without bothering to have to do a free fall experiment. All that you have to do, for example, to measure g acceleration due to gravity is take a pendulum of known length L, measure its period with a stopwatch, and then from there you can ultimately solve for g, acceleration due to gravity. You'll actually set up this situation involving a conical pendulum as a laboratory exercise to do just that. I'll have you use a conical pendulum to measure g. Okay, one last thing, however, about this problem, and that's the continuation to this problem in the lecture examples. Let me go ahead and position my screen. Okay, the continuation of the problem says, can the angle made by the string of a conical pendulum be greater than or equal to 90 degrees? Okay, let me illustrate exactly what I mean. I'm going to have to demonstrate this to you once again. I'm going to have to retilt my phone. So bear with me once again as I do this. Tilt this downwards. There we go. Okay, so now I'm going to go ahead and go beyond the small angle approximation. I'm going to manipulate the conical pendulum like this. Okay, is this a conical pendulum? Yeah. In this case, the angle itself is quite large. I could not honestly make the small angle approximation here in this situation. But what the question is asking is this: is it physically possible for the angle that is made by the string with respect to the vertical direction to be equal to 90 degrees? That means that the string is parallel to the ground, or be at a greater than 90 degree angle, which would look like this, and then the conical pendulum would circulate, for example, like this. Is this physically possible? No. Let me explain why here on the board. Once again, I'm going to have to tilt my phone to do so. Okay, now let me do some erasing here on the board. Okay, now let's just go up to the force diagram here. Watch what happens to the force diagram if we make the angle theta, for example, equal to 90 degrees. Then the diagram looks like this. Okay, here's the tension vector like so, in the same direction as the centripetal acceleration. Here's the force of gravity straight downwards. Here's the object itself. And then with respect to the vertical direction like so, right here is then the angle theta equal to 90 degrees. Notice that there is no component of tension pointing upwards to cancel out the force of gravity. So then therefore, if I was taking the conical pendulum and whipping it around my head faster and faster and faster, the string would approach a 90 degree angle, but the instant that it gets there, there is no component of tension pointing upwards, and then therefore it falls back down like so. So I can only approach the 90 degree angle, I can never equal it. What if the angle was greater than 90 degrees? Well, then the situation would be even worse. It would look like this. Okay, so let me make some adjustments here on the diagram. Now we'll make the angle greater than 90 degrees. That would look a little strange. Now in this case, the tension vector is going to look like that. And then right here is the angle theta like so, greater than 90 degrees. And now the situation is even worse than it was before, because not only do I have nothing pointing upwards to counteract gravity, but I also have to counteract right here a component of the tension vector that points downwards as well. So this situation is physically impossible for that reason. So what would this situation look like if I tried to throw this thing above my head and manipulate it such that the angle was greater than 90 degrees? You know, something that looks like that. Well, the object would just end up in free fall until the angle is less than 90 degrees. That would then just simply look like this, like so. Notice that when I did this, basically what happened immediately is that the conical pendulum fell downwards such that the angle was less than 90 degrees. So the answer to the question and the problem, can the angle made by the string of a conical pendulum be greater than or equal to 90 degrees? The answer to that is no for these reasons, okay? Okay, this is obviously a long problem. Let me go ahead and conclude this portion of the lecture here.